and welcome to another video. Now, you may wonder from the title, what am I talking about? Alternate quantum models or something like that? Well, this is because in my best received video that has gotten over 1,000 views, which for me is quite a lot, which I think I only got because I made it sound in the beginning or like from the title that maybe quantum mechanics isn't real. And I'm quite on the opposite side of that argument. I think quantum mechanics is an extremely well thought out theory, or it together with its additions, right, is a very well thought out theory. And yeah, so I have actually had 3 people who have written me after this video to suggest their quantum model to me. One of them actually exists as a website, so I would like to talk about this first. I got sent some kind of I guess I should call it a conjecture piece in Pages by someone else, and I have got sent a model by someone else who pointed me towards a more historical model or alternate explanation to quantum mechanics. And I would like to do some videos about those now that I have a bit more free time on my hand. I might be able to squeeze them out. This is the first one. Do not worry, the other 2 are coming. I know you've written me an email asking where it is, and I'm sorry, I'm so busy, but I will have a look at them. I promise that, and I will stick to my word, and here is the first one. So this is called The Simplest Universe, available on the internet via thesimplestuniverse.com. And first of all, I have browsed through this website a couple of times, and it's for someone who suggests an alternate quantum model. This is an extremely well thought out thing and an extremely well thought out website. Presenting your ideas in that way makes it extremely easy to get a hold of them, right? And I like that a lot. Now, I disagree with parts of your model. Well, not I, experiments disagree with parts of your model, and I will show that later, not to worry. But I must give praise where it's due, in that this is the best way to kind of convey your idea of a model, is by making a website that has countless animations. The sheer work that has gone into this is amazing. So kudos to you, right? I'm impressed. I couldn't do any of that if I probably could, but only if I learned everything of that, and like after a couple of years. And he actually keeps them updated. This has been updated not 2 weeks ago. So that whole thing, like you deserve some credit for that. Absolutely, right? Okay. So what is this simplest universe model? It's an atomic model that takes a different approach to modern physics. Than modern physics, really. And it's based on helical spirals, if you will. Now, again, I'm presenting this. I do not agree with this. However, for some of these things, it makes completely fine predictions. It's just another way to look at particles. But it fails at some predictions, and as far as I can say, there's no formalism behind it, and it doesn't make any predictions that are how should I say? It just doesn't make any predictions that would be new to us, and it even makes some predictions, as far as I understand it. And please, to the author of this website, please do correct me if I'm wrong. Right? I'm not here to say, oh, that's crap. I'm saying, oh, it's interesting, but it's wrong. And it makes a couple of predictions that I think are wrong, or that disagree with experiment. And as it actually has done here, if it disagrees with experiment, it's wrong. So, okay. Where to begin? It is a subatomic model. I already mentioned that. That is about helical particles. And for example, a particle of light is a pair of left-handed and right-handed helixes that just go on spiral. You can see this here on the website. I do encourage you to look it up. It is a very nice website to play around with. And you can even cut away these things to have a deeper look at them. For example, an electron is just a right-handed torus, a positron is a left-handed torus, and a neutrino is a single left-handed. So they already explain a couple of things with that. They can explain charge with the direction of the thing spinning. This is why light has no charge, and the positron and the electrons here have charge, for example. They can also see why neutral here as a neutron doesn't have any charge because the two are into each other. Oh, the light ray comes in here very slowly. And it explains that with these helixes, which okay, right? That's fine. Sure. Why not? Why not do that? You can even change the view for, and you can look at different things. For example, here's a proton, which is a positron held together by two neutral particles. Now, and I will show why I have a problem with this depiction specifically. This is kind of one of my two main criticism points, right? But I would like to introduce the rest before I go on. You can even see here there's a neutron, there's an antineutron. It all depends on the direction of the rotation, right? So far, even though it's a bit out there, I have no issues with that. It's kind of fun, right? Now you may ask, how do particles interact with waves? That's because they are kind of they are like two spirals, like in cogwheels, for example. They are gripping into each other and kind of turning the wrong way, right? And again, credit to that guy who did it. He has explanations for a lot of basic mechanisms on his website that, as far as I have looked at them, are completely fine, right? For example, how light interacts with matter, although this is work in progress, he says himself. I would like to briefly go about the electric fields, right? And there's even menus like that. So that's like, he clearly put some work into that, and that deserves credit, right? So let's say you have an electron in a negative field, and you can see here how this can become deflected. It's because the toruses interact with each other, or the spirals, the helical spirals interact with each other. And I do encourage you to look at this website yourself if you wonder how it works with that website, because again, there are multiple explanations of that. Unfortunately, though, I have to criticize it at two very, very vital points. The first one is their explanation of the Stern-Gerlach experiment. Now, the Stern-Gerlach experiment was an experiment conducted in the 1920s, thought of by Otto Stern and carried out by Walter Gerlach, who, by the way, Otto Stern got a Nobel Prize, not for that, but for something else, but he's a really important dude. And the way that they explain it is essentially that, well, they have an animation here, I thought they had an animation here. There it is. The way that they explain it is essentially you have electrons of a different spin that interact with the magnets, and they just kind of align differently depending on the direction that they are already spinning. Unfortunately, this goes against what we know from quantum mechanics, and I shall show why. I just let the animation finish. Now, the thing here is, you can see, depending on the angle that they come in, they end up in two different camps. But, and this is the huge, actually, problem, is that when you have those up here right now, you could see in that video, I'm not going to replay it, you can see in that animation that if they came 90 degrees, like so kind of if they fit perfectly in between the two magnets, if they came in between there, they went a certain way all the time. And that's a problem, and I shall explain to you why in my trusty OneNotes notebook. So, here we are back at my OneNotes notebook, and so I would first of all like to explain why what the Stern-Gerlach experiment actually was, or the Stern-Gerlach experiments, and why the simple universe model, which I will abbreviate here as SUM, fails at this point, as far as I understand. Again, feel free to correct me. So, what's the Stern-Gerlach experiment, or the experiments? First of all, those are the basics. You have an electron beam, and you have two magnets, one north and one south, or one magnet really. And the idea was that the electrons, depending on what spin they have, will go someplace or another. What we actually measure in that experiment is that there are only two locations where they end up. One of them is up here, one of them is down below, and in the middle there's nothing. Nowadays we know that this is actually due to the spin. This has h bar half, and this has minus h bar half. H bar is the reduced, or I think it's called reduced, Planck's constant. It's just Planck's constant divided over 2 pi. And so this is what we get today. What would be expected from classical ideas would be this red curve here, that we have kind of a Gaussian distribution in between, that most electrons have little spin and would accumulate in the middle, and some have more spin and would accumulate towards the edges, right? But this is not what we get. We measure this. So something's off. The classical prediction here clearly is wrong. What's going on? Modern physics can explain this. It has to do with that the electron only can have a spin of plus or minus. It has nothing in between. It's quantized, so to say. The spin is quantized. And by the way, this is the way that we got introduced quantum mechanics at university 4 years ago now, when I took the Introduction to Quantum Mechanics course. And so this is fine. The simplest universe model here works fine. We have seen their explanation. It predicts half-half split, presuming that the electrons that come in are already arranged randomly. And that's the issue. Because you talk about the first Stern-Gerlach experiment, and then you ignore the other two completely. And this is sad, because the other two, unfortunately, get rid of your helix model, right? Okay, so what about the rest? What about the rest, though? Okay, first of all, the second thing that they did is they put two of these two of these devices back to back. So we have here, I have abbreviated this to Stern-Gerlach Z, and Z means on the Z axis, because it depends how you orientate the apparatus, right? That you can either measure the spin in X, Y, or say Z direction, and they have nothing to do with each other, right? So our prediction would be that, well, we have a Stern-Gerlach experiment that measures the spin in the Z direction. We block half of it. So this is just absorbed. We only allow the positive spin to go through. We put another Stern-Gerlach device there, and would you look at that? It's still at h bar half. It's still at only the positive spin. There is no minus h bar half, no negative spin coming out of the second measurement device. This checks out, right? We have filtered out all of the electrons that don't have positive spin. Only these ones are allowed through, so obviously only those are measured. This checks out both in the simplest universe model and in quantum mechanics. And now is a problem, because this doesn't check out anymore with the simplest universe model already. And that's not even the worst part. So you have an electron beam going in. Again, we have a measurement device for the Z direction. We block out the negative spin. We only allow the positive spin to go through. And then we measure it in the X direction. Completely different direction now. This has nothing to do with Z anymore. And in the X direction, we get, again, a plus and a minus spin. In quantum mechanics, this is fine, because the X and the Z coordinates have nothing to do with each other. Something can have a spin in X direction and a completely different spin in Y direction. They are completely disconnected from each other. I would love to go into more detail about how we know that and introduce the Braquet formalism and how we do that in quantum mechanics. Unfortunately, this is not the scope of today's video, and it's also pretty complicated. So in quantum mechanics, this works. In the simplest universe model, I'm afraid we have to stop here already, because, as we saw in the animation, all of the ones that were orientated this one way would only exit in another direction this way, because it depends on the direction that it comes in with. So it would only be positive or negative, not both. And now comes the cracker, right? You put one in the Z direction again, you block out the minus spin again, as before. You only let the positive go through. You do the same thing with X. So we block out the minus Z, we block out the minus X, and then, after we measured the X, we measure Z again. And would you look at that, the minus spin is back, even though we blocked it up here. What's going on? Physics is clearly broken, right? No. What's going on? Quantum mechanics can actually manage this question. This was the onset of the quantum mechanics formalism that we have today, brought on, for example, by Paul Dirac and again Otto Stern and all of these lovely people. And the way that quantum mechanics deals with it is, well, when you measure the X spin, you destroy the state of the Z spin. And thus, after you have destroyed the measurement for the set spin can take any value again, because you've by measuring the X spin, you have destroyed all measurements for the set spin. And so it can take on any value that you want. Destroyed, maybe a harsh word. Reset all of the measurements for this set. Again, quantum mechanics can manage this, and this is so manageable that we use this as an introduction to quantum mechanics. In like the first 2 weeks of our introduction to quantum mechanics course, we were able to explain that using the formalism of quantum mechanics. So this is really in the very beginning. And unfortunately, the simplest universe model doesn't touch on this at all. And that makes me a bit sad, because I kind of like it. I don't want to lie, right? Doesn't talk about it, and unfortunately I think it fails here. So that's my first problem. What's my second problem? Okay, so what's my second problem? My second problem is a proton, or general composite particles. So you have here their explanation for a proton is you have these two rings. The first two are kind of intertwined, and there's a positron in between. I don't know why a positron, but okay, it gives it its charge, I suppose. And that's where the problem is. So wait, let's do a cutaway. Yeah, exactly. So you can see better. So you have these two intertwined ones, and there's a positron in the middle. Unfortunately, this is not how protons look, and I will explain to you why right now. Okay, so as we saw from their animation, they have two intertwined toruses that are, in our terms, charged neutrally, because we saw that the charge is dependent on which way the torus turns, and because they have two intertwined ones, the net rotation is zero, the net turning rotation is zero, if you will. And then there's one positron in the middle. Now a positron is one tiny particle. I do apologize, that was my computer again. I hope you didn't hear that. It always happens when I record videos. The proton has what's called a magnetic dipole moment. What's that? Okay, so this is a proton, or our understanding of a proton. It's composite of two up quarks and one down quark, and gluons gluing the whole thing together. The two up quarks have 2/3 of an elementary charge each, and the one down quark has -1/3 of an elementary charge, resulting in one elementary charge, the charge that a proton and also a positron has. So far, that's fine. Now it's the issue. The center of the proton doesn't line up with the center of the charge. It's not really center of the charge. I just don't know how else to explain a dipole moment, really. It's a charge that's not sitting perfectly where the center of mass is. And that's an issue, because in a positron and in an electron, we haven't found a dipole moment yet. If there is one, it's so tiny compared to a proton, because in a proton we can measure one. How do we measure that? Well, you have a torque, you have the magnetic dipole moment, and you have a magnetic field. So you apply a magnetic field to a proton, and you can see that the proton aligns like a magnet to this kind of magnetic field, according to the field lines. And this is a tiny force which is called a torque, and we can measure this torque. And that's the issue. The torque can be measured for protons. So far, it cannot be measured for electrons, and thus also not for anti-electrons, which are positrons, right? This is contradictory. Your idea of a proton contradicts modern measurements of proton dipole moments. And that's unfortunate. I don't think it's possible in the simplest universe model. So with that said, I think we'll leave this model here. There are a few more things to say about it. None of them are that interesting. But again, to the guy who did that, kudos to you. Your website is very well thought out. It was a bit confusing at first to navigate it, but once I understood it was very straightforward. And you're putting all this effort in there, and I applaud you for that. That seems like a lot of work. Unfortunately, it has problems. Stern-Gerlach experiment and the proton dipole moment are just two that I could immediately think of without going through all of your website even. So, man, I'm sorry, but I don't think that this is the one. Also, your model kind of doesn't make any predictions that would lead physics further, right? Where are your predictions that could be tested? And if you just reinterpret already established knowledge and build a model around that, which technically, right, you can do, it should, of course, agree with all experimental findings so far. If you do that and you don't make any predictions, it's not better or worse than the other model. It's just kind of the same. If two models make the exact same predictions, they're the same for practical purposes. So, but yeah, still, this was by far, that much I can already say, by far the best one that I got sent. So again, kudos to you and your website. But yeah, I think I will leave this video here. Thank you so much for watching. If you enjoyed this video, please consider leaving it a like. If you enjoyed a lot, please consider considering subscribing. And I will see you in the next video. Until then, have a nice time. Goodbye!